Hello, y'all. Darrell Lee Berry Jr. here to do some quantum mechanics. So we'll do some perturbation theory. I'll work through several problems. I plan on being here several hours, either in one time or maybe I'll break it into a few sessions, and we'll just go from there. So, looking at the screen, we'll go ahead and get started. So we'll start with a problem. Uh, so let's say that we have a well, an infinite square well. Let's say that we have a perturbation in the well. So the well is, let's say, 8 uh, A long. And let's say we have a perturbation here. So the perturbation is on the left side of the well. And let's say the perturbation actually goes to four, 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 4/8 A. Guess it'll be 4/9, let's say. So about 4/9 of the way. And we'll see how this goes. Now, perturbation theory is actually, you can actually work it out in a few pretty straightforward formulas. I'll pull up one here. So let's say we wanted energy, the energy of uh, the state, the change or the difference in energy, because we know that we have an infinite square well, the psi will look like this. Psi of x equals a sine kx. And that's pretty much just the default equation for an infinite square well, how the equation will look for psi. We can go ahead and put out the Schrodinger equation. Basically, we'll have negative h bar squared over 2m psi double dot plus v psi equals e psi. And if this thing is with no perturbation and this was 0, then we know we'd have psi double dot equals 2m e over h bar squared with a negative here and a psi. So that'll end up being our coefficient on the side. So basically we would call this k squared equals 2me over h bar squared. That'll be pretty much the default uh, wave number, you can say. And the difference will be, because there's a perturbation here, maybe I'll do this perturbation a bit too high. Let's make the perturbation a little bit lower. If we have this perturbation here, it will alter the energy by a certain amount. So what we can do is we can calculate the correction to the energy, like what the energy difference will be, because you could imagine that if there's a wave here it'll be that side to be boosted up somewhat. Like something on this side will cause that wave to be higher because the potential over here is higher. There was no potential. It'll basically, fill the well like normal. But since there's a boost here, this side is going to be higher. So what we want to do is get uh, the change in energy. So here, normally we would have, it was a empty well, and we solve for this key right here. It will end up being n pi x over a sine, and this will end up being the the after we solve for boundary conditions. So our k will end up being uh, k squared equals n squared pi squared over a squared, which will equal 2me over h bar squared. So this means that we solve for energy, we'll end up having E, and this is the default energy, E equals n squared pi squared h bar squared over 2m h squared. So this will be the energy of the waves inside, the wave functions inside this well, if there was no perturbation. But now what we have to do is we have to figure out what boost will this potential that's added here cause to that. So the equation for that would be this. It would be En for whatever value of n we want to choose, and 1 for the first level perturbation. Basically, we'll be using this equation to solve what the new energy is. And what we're basically going to do is we're going to take the initial wave function, whatever energy we want to use, and we're going to put the perturbation and take the expectation value of that. So the expectation value of the perturbation is going to give us the boost in energy that we have to add to find out what the total energy will be on that side of the well. So we can basically call this En. This is En naught, the default energy, if we did not have a perturbation. And this is the correction to the energy, meaning how much this energy would increase on this left side. And let's say that the energy over here is V naught. So there's a potential on this side with an energy V naught perturbing the well of this particle in this infinite square well. And then we're going to find out what the correction is to add to the default energies to find out what the total energy is of that well. Now, this notation refers to two integrals. At least one integral or two parts. So that's why we had to get the original wave function, which is this. If we was to solve for it, I forgot my coefficient. This coefficient A will end up being square root of 2 over A if we solved all the boundary conditions. And I believe on one of my earlier videos, I'm certain I solved for this. So I might be going over some of the earlier parts to scroll through some of the earlier videos on the channel. And you'll be able to see when I solve for some wave functions and like solve for infinite square root. I'm sure I did that. So you'll be able to go to those earlier videos and see the background to the default setting. And now what we're doing is altering that setting. So now that default energy has a perturbation on it. So we take our default wave function, which is square root of 2 over A sine n pi x over A. And let's say we want to do the first, the lowest state, right? So let's say n equals 1. So that'll make that 1 pi x over A. Perturbation is V naught. And then we have square root of 2 over A sine pi x over A dx. And we're going to integrate this over the entire well. But the thing is, V naught, which is H naught, or H prime, is only between 0 and 4A over 9. So that means that since I'm integrating the expectation value of that perturbation, I need to end my boundary there. I'll square these two coefficients. So that's 2 over a. Those are the same. So it's psi squared pi x over a. V naught is a constant at this point. So I'll put that in the front. We have dx. And this integral, you have to basically use the half angle formula. So we have, and I'll actually put this in the front as well. We have 2 v naught over a. And we have 1 over 2 minus cosine 2 pi x over a over 2 dx. And then we'll go ahead and integrate this. So we have 2 v naught over a. We have x over 2 minus sine 2 pi x over a divided by 2. And I'm going to have to take the derivative of this in here and divide by it. So that'll be times a over 2 pi, taking the derivative of this with respect to x. And we're going to have the 4a over 9 and 0 for the, what we insert into this, right? And let's check, let me make sure I didn't make any errors on my algebra. Everything seems to be good. See what we have when we put this in. So we have 2 v naught over a, and we have 4a over 18 minus sine 2 pi 4a over 9. So that'll be a 4 9 2. Then a over 2 pi minus, then we got to put a 0 in for x, and sine of 0 is 0, so that's just going to be 0. So we have 2 v naught over a, 2a over 9 minus, so I'll actually put this in my calculator and see what this is. The 8 pi over 9 is what that'll be. Divide that by 2. So we have 0.024 a over 4 pi. So we can see that the a's will all cancel. So what we end up with is 2 v naught 2 over 9 minus 0.024 over 4 pi. So that means that this is the increase of the energy. So E1 total would be, and since that was a 1, we chose 1, pi squared h bar squared over 2m a squared plus 2 V naught 2 over 9 minus 0.024 over 4 pi. And if you have any questions, I'll be checking the chat here. So be sure to drop a line, those of you who are watching. I know if you understand or have any questions, and that's that. So now we have what the energy would actually be on this side, on this portion of the well that's perturbed by that energy. Now I actually want to take a look at an integral for the default problem and remind myself what the deal was with that integral to make sure I did it properly. It's going to be over a after you square that. So let's take a look and see what this integral is. And this is like normally you end up with like half a well. So for instance, a over 2 to a. So this would be equivalent of the well of the perturbation went from here to there. So the perturbation goes from a over 2 to a. We'll see what the perturbation will be. So now this is the perturbation. A over 2 to a. So we have the V naught here. We have the sine squared n I x over a dx. And we'll take the integral for any value of n. So we have the same thing, 2 V naught over a. We have the integral a over 2 to a of 1/2 minus cosine 2 n I x over a over 2 dx. So if I take this integral, we have 2 V naught over a. We have x over 2 minus sine 2 n pi x over a over 2. Divide by the derivative of that. So that's a over 2 n pi and a over 2. All right, so when we plug this in, we have 2 V naught over a. We have a over 2 minus sine of 2 n pi over 2. And we have a over 2 n pi minus, so 2 V naught over a. And we still have a over 4 minus sine of n pi x over a. Right, so that's our two integrals if I did that properly. Take a look and see if I missed anything. Oh, I still wrote the a again, no mistake. Just going. We also still have a divided by 2 on that. So let me just put that on the outside. Actually, let's erase that. 4, 2. All right. So sine of 2 n pi, sine of any n pi is going to be 0. Because sine of 0 is 0, sine of 2 pi is 0, sine of 3 pi is 0. Over here to be the same thing, sine of 0 is 0, sine of pi is 0 sine of 2 pi is 0. And I remove the x. So that means that its signs will leave terms of 0 out. And we still have 2v naught over a. It's a over 2 minus a over 4. So that's 2v naught over a. 2 a over 4 minus a over 4. That is going to be 2v naught over a. And 1 over 4. That's going to be v naught. The a's are going to cancel. V naught over 2. So that means that for the half of a well situation, the energy is going to be, or just E, N is going to be E N naught plus V naught over 2. So those are two examples of the perturbation of an infinite square well with a potential on part of the well, like an extra potential that's lifting the well. All right. So let's see what we have next. All right. In a moment, I'll find which problem we'll do. So I'll go ahead and note it here. We did that one just now. Okay, so let's do this one. A two-dimensional perturbation, right? Which is a little more complicated. This is problem 2.2. So we have a 2D box perturbed. So basically what it's looking like is, if we're looking down on the situation, so that we're looking down on the well, we have a two-dimensional box. So this is X, this is Y, this is 0 in both origins, and we have widths and heights of A. So this is A, this is A. And if we have a perturbation, let's say we have a perturbation in the X part from 0 to A over 2, and then the Y part from, let's see, from A over 4 to 3A over 4. This is our perturbation. So what we're going to do here is we're going to go ahead and do what we did before, but now we have a 2D box. So psi is going to be psi of xy, which is going to be a bit more complicated. So then we have psi in x in y and psi. And actually, let me make sure I'm writing that properly. Mm, mm. All right, here we go. So basically, we have psi xy, which means we're going to have psi in x in y here. So it's going to be psi in x of x and psi in y of y. So now each of our wave equations here, we had a one-dimensional box uh, with A. We just called this with X, and that was fine. All right. Now we have a two-dimensional box. So we have basically the wave function is a function of X and Y. Now we have to take both of those things into account. So the wave function will have X and Y components to it. And we can actually use the same situation we had before. We can't see it as well, but we still end up having a situation where we have X here, we have Y here, but now we have a perturbation that's in this area here going upward. So you imagine on this little area here, the perturbation is going upward, and we have a wave function that's basically three-dimensional that's going to be boosted in that area. So we want to find out the perturbation to the energy at that point. You can imagine this is a uh, basically a three-dimensional well with a two-dimensional wave function. Right, y'all are with me. So we can actually use the same wave function that we had before. Psi of I equals square root of 2 over a sine I pi x over a. So I will be either x or y, and this is going to be our function. And the way it works is we have psi a and we have psi b. So psi a will end up being, so basically, if I was to back up a little bit, we could look at this several different ways. So we can have psi 1, 1, in which both x and y have 1. So remember, we're going to be psi in x and y. We can have psi 1, 2 and psi 2, 1. These are called degenerate states because being that the wave functions are the same, it's a balanced two-dimensional box, they will have the same energy. Or we can have psi 1, 3 and psi 3, 1, which also are degenerate. We can have psi and so on and so forth. Psi 2, 2. There's only one version of those. But if you notice, this is actually degenerate with this. Well, at least it looks to be. It has the same number of n values, so we have to calculate it and see if it's actually degenerate, but you see what I'm saying? So that's what we're looking at. So maybe it's degenerate, but it's going to be n squared, so it probably won't be, but it gets a bit complicated when you actually do the algebra. So what we'll do is we'll pick the perturbation. We'll do the lowest energy degenerate pair. So, and maybe I should do the non-degenerate first. We'll see about doing both. So there's only one, one, one. Let's see what that one is going to be like. So we have psi 1, 1 equals equals square root of 2 over a, and we have sine oh, let me make sure I got my notation right there. We have sine of 1 pi x over a, and let's call the potential v naught again. V naught, and square root of 2 over a sine of 1 pi y over a dx dy, and I may be missing one of my signs. Put up here. Let's copy this one over. View what we have here. Boom. Dx dy. So what we have is, as we wrote up there, psi in a two-dimensional box is in x and y, like y. So one side is going to be whatever psi of nx we're going to do, x, and one psi of ny we're going to do y. So we know from the first problem that if the energy is non-degenerate, the perturbation is going to be this, the change to the energy. And in this case, psi n naught equals psi nx ny xy, which means it equals psi nx x psi ny y, which means now I'm plugging in this psi nx ny xy, and v naught for the perturbation, and psi nx ny xy, and now we can get the perturbation off that and see what the value is, right? So everything is looking good. So let's see what we get. Oh, we have my integral, and I'll put the bounds in momentarily. So let me actually separate these, and we'll end up having 2 over a integral x is from 0 to a over 2. And we have sine squared pi x over a. V naught still goes to the outside. It's going to be dx. We have integral, and y, the perturbation is from a over 4 to 3 over 4, and I wrote that backwards. This will be 3a, and this will be a. A over 4 to 3a over 4. So now we have a over 4, 3a over 4. We have, left off my 2. We have 2 over a sine squared pi y over a dy, and these are our two integrals. And let's see what we end up getting. So we have 4 v naught over a squared, integral 0 to a over 2 of 1 over 2 minus cosine 2 pi x over a over 2 dx, and integral a over 4 to 3a over 4, 1 half minus cosine 2 pi y over 2, this is over 2, over 2, excuse me, this is over a, that, over a, and dy, right? So this is our half angle formula, but we did it in sort of a double framework. Since it's not actually a half angle, it's a full angle, so you have to double the angle, but the process works the same. You can look up trig identities if you're not familiar with that. So now let's go ahead and take our two integrals. We have 4 v naught over a squared. We have x over 2 minus sine 2 pi x over a divided by 2. We have to again take the derivative of the middle part here and divide by that. So that's a over 2 pi. And this is from a over 2 to 0. And over here we have y over 2 minus sine 2 pi y over a over 2. And this becomes a over 2 pi and 3a over 4 and a over 4. And we'll see what the energy is here. So we end up with 4 v naught over a squared times a over 4 minus sine. So the a's cancel, the 2's cancel, pi x over 2, a over 2 pi minus 0. So all of that's going to be 0 times, I'm going to have to write these out, times 3a over 8 minus sine 3 pi 6 pi y over 4 over 2 a over 2 pi minus a over 8 plus, because there's already a minus here, sine is going to be a's cancel 2 pi y over 4 4 pi, and a is in the front. Right, so I think that's right. If it's not, somebody drop a line and let me know. Let's see what we have here. We have 4 v naught over a squared. And we have, so this is going to, left off my nx. There is still a n there. And so in this, I can put my a there. Make sure I didn't mess that up there. A's cancel, 2's cancel. Yeah, so that'll just be pi. And that's going to be 0. And technically, I'm doing this for all n's. Oh, no, I already made this n equals 1. That's right, I forgot. So sine of pi is 0. 1 zeros out. So we have a over 4. This is going to be times 3a over 8. Minus, all right, so this is going to be, oh, I'll still put the y there. Six, five. Yeah. So let's put this in a calculator and see what this is. I could do a unit circle. You could check one of the videos I did a unit circle, but I actually don't feel like doing a unit circle at the moment. Let's focus on the quantum mechanics. So divided by 2, this ends up being 0.04. Oh, times a over 2 pi, a over 2 pi, minus a over 8, and plus, so that's power over 2, so that's going to be 1. I don't need a calculator for that one. So that's a over 4 pi. And we know that, oh, it's going to leave, oh, that's right, there's an a squared there. That's a little bit ugly. So I believe we can use this to cancel all of the a's straight off, because this is basically 1 over a times a. And if I distribute this 1a here, it'll get rid of that. And I distribute this 1a there, it'll get rid of all of those a's. So that should take care of that. So now we have equals 4 v naught times 1 over 4. And actually, I can actually get rid of the 4 right there. That takes care of that. And we have 3 over a 8 minus 0.04 over 2 pi minus 1 over 8 plus 1 over 4 pi. So that's going to be v naught. Now let's see what that is. Right. So that's not too bad. 0.57 v naught. Now let's compare this to, let me close this. So let's compare this to the previous answer. We had a two-dimensional swirl well, and when I did the half of it, we got that. When I did the very odd portion of it, we got this. Let's see what that is, by the way. So this part here is 2 times 2 over 9 minus this. So that's 0.44 v naught is what that is. And here, so basically that's what? A half of V naught is about a half of V naught. So we can see that it's about the same. So basically, if you remember, this was 4/9. So this is about a half, right? 4/9 A is about 0.5 A, close enough. So it makes sense that uh, that little bit, less than a half, will give us a little bit less than a half of the boost to the energy. The precise half will give us precisely a half. And here we have a little bit more than a half. So looking at this, it's interesting. So I would think it would be slightly less. Let me see what the default problem didn't do. This problem in particular did I did do what do you call it? Degenerate one, but it should give you pretty much the same answer. Let's see what the default one had as an answer. Oh, well, they have V naught. So the default one, which is um, the degenerate energy, so it's a higher up energy, so it should be a little bit higher. But it is V naught over 4, 1 plus 2 over pi. So let's see what this actually is, and we'll see what the difference is from the default level to the higher up degenerate level. There's going to be 1 over 4 times 1 plus 2 over pi. All right, so this is 0.41 V naught. All right, think about that. So that's the state where you have 1, 2, 1, 2, not the ground state. The energy of the default well is E equals n squared pi squared h bar squared over 2 m h bar squared. So it should go up. Maybe I did some incorrect algebra or something on here. Close enough. I mean, it's in the same ballpark. You're not making too much of a change from the well. Still, it seems like it should be lower than this energy, but I can't really say I have a great intuition for perturbation theory yet. So, but that's what I got. So let's see what the next problem will be. How long have I been going here? About an hour. Maybe I'll do one more problem and take a break and come back. Let's see which one I do next. And actually, the next problem is going to be fine structure. That's a big change. I'll come back and do that. It's going to be a bit longer. But I might take an hour just for that problem. So why don't I take a break here and expect me back in like 30 minutes or so. And we will do as a fine structure perturbation where in the initial part of quantum mechanics, you deal with, I guess you can say, whole level changes in energy. But when you take a particle and you put it, let's say, in a magnetic field or an electric field, the electric field or the magnetic field can cause certain interactions with the magnetic moment interactions of the electrons and protons. So, for instance, if you have a hydrogen atom and you have the nucleus here, right? And you have an electron, minding its business out here, being all wavy, but I'll draw it as a particle. Well, an electron has either a spin up or a spin down, and that's sort of like a magnetic moment. And Photons have spins as well. So these magnetic moments can align or not align. And if we put them in a magnetic field or an electric field, it's going to cause them to align or not align more so than not, one of the other ways. And basically, the interactions between these two will take degenerate states, like I had these states here that were degenerate, right? They have these same energy. It's just basically 1 in x2 and y will give you the same energy as 2 in x1 and y. So, but when you put them in a magnetic field, because the spins are different, uh, the down one will have a slightly different energy than the up one because the way the spins are. So what'll happen is these degenerate states that were the same before will now have slightly different energies. And it ends up happening where uh, I believe I showed, maybe it was a few months ago, some spectra of the sun where you was able to see spectra of, for instance, sodium in the sun. Well, the fine structure would make it so that if we zoomed in on, let's say, this point, we would find that there's actually a lot of structure in that point if you zoom in. And this will be what fine structure is that a magnetic field or an electric field can do, which will break these degeneracies and cause multiple uh, slight different variations in energy for certain quantum states. So we'll look at that in the next video when I'm back in about 30 minutes or an hour or something like that. And I'll see you all then. So like, subscribe, share if you haven't already. I'll see you all in a bit.